Hello, this is Caleb on electrical. Today we're looking at some of the design specifications we considered in designing our switch mode power supply. And as you can see on the screen, we have our circuit already put together there. So I'll be taking you through the components we used and the design criteria we considered when putting them together actually. So on the screen we have our DC to DC back converter there, which steps down the supply voltage down to about 12 volts. Then we have our controller, that is an SG3525 controller. We have our port there. The port is used to regulate the frequency because this is a test design, so we need to regulate our frequency down. Then we have our driver. Then also we have our MOSFET transistors. We are using an RF 3205 MOSFET transistors. Then we have our power transformer, then our rectifier stage, then our filter, inductor, and a capacitor, and also a feedback resistor and a potentiometer that senses the output voltage and gives in the reference voltage to the controller. So basically that is the component we used in our circuit there. So this actual schematic we used. Then we have a transistor there, the pull down resistors, the gate resistors. Then we have these resistors and capacitors on the collector. We have the primary windings with VCC, which is about 19 volts, and the secondary windings and the rectifier diodes. Then we also have an output inductor, which is about 100 turns, and a 0.4327 centimeter core, which is a powder core. Then we have the filter capacitors, which is about 4,700 microfarads. Then output LEDs and feedback resistors. And we have C4, which is about 104. That sends a voltage of 5.3 voltage to the microcontroller. In our design conditions, we have a controller which is SG3525, variable output voltage 6 to 30 volts. Then we have a VCC range which is about 14 to 22 volts. We wanted a power of 100 watts or more. And the core type we use is an EER core. Now for the calculation, we calculated the area of the core. Because it's a cylindrical core, we use our pi r square, which is about 1.34782 centimeter square. Then we selected our frequency to be 35 kilohertz and a parameters of 16. So this is a pre-selected value, or this is a pre-selected calculation. At 14 volts input voltage, we had a flux density of 123.658 gauss, which is at 14 volts. Then at 22 volts, we had a flux density of 1943.2 gauss. From a VIN of 14 to 22 volt. Now I did this just to because I knew our actual operating voltage for VIN will be somewhere between 14 and 22. So I designed it this way so that our flux density will be between 1200 and 2000 gauss, which is a flux density condition for ferrite cores. So with the bipolar winding, we did 6 turns with the 6 copper wires side by side. Now for the secondary voltage, now we selected the headroom of 33% of maximum output voltage allowed. The maximum output voltage is 30 volts, right, which is our voltage in we selected here from 6 to 30 volt. Then a headroom of 10, which is 33% of that 30 volts. Now when you add it to it, the actual output voltage should be around 40 volts. So we have a headroom of 10 and our maximum output voltage we want, which is 30 volts. Now this design is for a variable output. So that's the design. This design is for a variable output. Now after that, our end secondary, the number of secondary turns will be equal to the 40 volts, which is the secondary voltage we want, divided by 18 volts. Now the 18 volts came as a result of when we find 22 minus 14 divided by 2. So we look at the midpoint of this one, and that will be around 18 volts times 6 turns, which will give you 13 turns. So it means that for bipolar windings on the secondary, 13 turns, wound 4 copper wire side by side. So that's what we did.